Last time in phase equilibria, we discussed how to calculate the fugacity of a vapor or a liquid phase if you were given an equation of state. Recall that the usefulness of this is because you can apply the equilibrium criteria that the fugacity of the vapor has to equal the fugacity of the liquid if the phases are in phase equilibrium. You would do that by applying either one of the following two equations. So ln of phi is again F over P. And you would apply whichever one of these would make the most sense for your equation of state, or for whichever one was easiest to calculate. Today what we'll discuss is how to calculate the fugacity if you don't have an equation of state. So a question you could ask is, what if I have a a liquid or a solid with no equation of state? So while the Peng-Robinson and the Suave-Redlich-Kwong do work well for vapors or liquids, there are some equations of state that do not correctly model liquids, and there are basically no equations of state that model a solid well. So we have to be able to model solids, liquids, and vapors, and what we'll discuss today is how to model the liquids and solids, especially when no equation of state is available. This is called the Poynting correction. Poynting correction, and it is for, again, calculating the fugacity of a liquid or a solid with no equation of state. Calculate fugacity of a liquid or solid with no equation of state or at high pressure. So let's think about this in terms of an example. So try to estimate the fugacity of liquid water at 25 C and 1000 bar. And again, we're not going to use the steam tables in this. We're only going to use the following information. We have the vapor pressure of water at 25 C is 0.0317 bar, and the molar volume of the liquid at this temperature. So this should be at 25 C as well. Okay, so how do we go about estimating the fugacity? So first thing we have to do is ask ourselves if we know the fugacity at any point. And if we know the fugacity at any point, we can use the equation that gives us the change in fugacity. So we're given that the vapor pressure at 25 C is 0.03 bar, which is very, very low. So at 0.0317 bar, this is a very low pressure, so we can assume ideal at this low pressure. Therefore, the fugacity is going to approach P for ideal. And therefore, we can say that the fugacity of the vapor phase at 25 degrees C is 0.0317 bar. And because we have P star, that is P saturation, that's our saturation pressure, that's how we know we're at phase equilibrium. And we can also say that this is equal to the fugacity of the liquid at 25 C. And that is a good starting point. So now we know the fugacity at one point. So I should also say this is at 25 C and 0.0317 bar. Right, and now we want to calculate the fugacity of the liquid for 1000 bar. So we're undergoing a pressure change from this low pressure to this high pressure. All right, so what next? If we had all the other thermodynamic properties, we have fundamental property relationships for. That's usually a good place to start. For fugacity, we don't necessarily have a fundamental property relationship. So let's start with the definition of fugacity. So remember, I wrote this a couple videos ago. It said that the ln of F over P is equal to the Gibbs energy minus the Gibbs energy of the ideal gas. Oh, and I'm also going to start using the book notation a little bit closer. I realize that when I write star, that could either mean for an ideal gas or for saturation, and I don't want to confuse things. So I'm going to start writing IG, or trying to, for the ideal gas situation. All right, so this is our definition of fugacity. And typically what we do after this point is we take the derivative of the entire function such that we can calculate what the changes are. So we do this all the time. Like if we had Gibbs energy, for instance, remember we could say that Gibbs is equal to Gibbs is H minus TS. And then we differentiated that, and that got us to derive dG is equal to V dP minus S dt. So I'm just trying to draw an analogy to what we're doing here. So before, we would write our fundamental property relationship for the thermodynamic property of interest. Then we would calculate the change in that property with respect to certain independent variables. All right, so same thing that we did before. We're just starting with the definition of fugacity. And now I want to differentiate this to get us the change in that property. So differentiating now. Differentiate, that gets us, it's just going to be d ln of f over p on the left-hand side is equal to, now Gibbs is going to change here, but temperature is staying constant. So for constant T, I've got 25C and 25C. So there is no temperature change. So here I would have to do the chain rule, but because I don't have a change in temperature, I can treat temperature as constant, only for this particular case. So it's dG minus G ideal gas over RT, and I'll make a note that only if T is constant. And use chain rule if not constant. Okay, so now we've got a change in Gibbs minus ideal Gibbs term. So how do we go about calculating that? Well, we can use the same fundamental property relationship that I just wrote above. So I can use this one with keeping in mind the fact that there is no change in temperature. So it's just dG is equal to V dP. And I can also say that the change for the ideal case and dG ideal gas is equal to V under bar ideal gas dP. Okay, what next? So I know what the molar volume of the ideal gas is. So I'm going to plug that in. So remember RT over P dP. And I'm not going to evaluate that just yet. I'm going to leave the molar volume for the liquid. So I'm going to just plug these two terms into the equation above this one. So it's d ln of F over P is equal to V minus RT over P dP over RT. And then we can, before we integrate this, we can simplify a little bit. So we can say it's V over RT minus 1 over P dP. Now we are to the point where we can integrate. So if we now integrate this such that we can get our change in ln of F over P term back. Let's see. I want to integrate from the limits of P1 going to P2. All right, so taking the derivative of this term just gets me this back again. ln of F over P from P1 to P2 is equal to, I have a constant here, so I can just put, it's Vp over RT. I wrote that backwards. It's usually PV over RT, but this will work. Minus, I've got an ln of P now because it's 1 over P. And this whole thing is being evaluated from P1 to P2. All right, so next I'll plug in the limits of integration. So everywhere where I got a P, I plug in P2, and then I subtract the value at P1. So applying these limits gets me ln of f over P2 minus ln of f over P1 equals V P2 minus P1 over RT minus ln P2 over P1. Okay, now I know what P1 is. I know what the fugacity, oh, I forgot my subscripts here. So the fugacity is in general going to be different at the different temperatures. So I have to keep my subscripts there. So it's fugacity 1 over P1 and fugacity 2 over P2. I know pretty much everything in this equation now, right? I know what the temperature is. I know that this V, I have to keep track of this. This is the molar volume of the liquid. Remember where this came from. This is coming from there, molar volume of the liquid. I got to keep that in mind. And that was given in the problem. I've got the pressure from the problem. I've got the pressure of interest from the problem. I've got the gas constant. I've got the temperature, and I've got everything. So I can simplify this now, and I can end up with, when I take two ln's minus each other, remember there's a fraction there. So my simplified expression is f2 over f1 equals the exponent of v under bar P2 minus P1 over RT. Just to show you the intermediate step, the left-hand side simplifies to ln of f2 over P2 times P1 over f1. And then because I put this on the other side, right, so I'm going to say plus ln of P2 over P1. And now I can multiply these things together. So it's ln of f2 over f1 times P1 over P2 times P2 over P1. And the P1s cancel, P2s cancel. I'm off with ln of f2 over f1 on the left-hand side, which is where this came from. So this term in the exponent is called the Poynting correction factor. This is what it actually is. Poynting correction. And importantly, this allows us to be able to calculate the fugacity at some second set of conditions, given constant temperature, given the molar volume of the liquid, and given the fugacity at that point. All right, so because the conditions of interest are most frequently known at saturation, so typically the fugacity is known at the saturation pressure at Psat. All right, so we say that the fugacity at Psat is F saturation, or just Fsat. All right, so plugging that stuff in, plugging the F1, or taking the F1 over to the other side, I'm left with the way it's typically written is that the fugacity at whatever point, so I'm going to get rid of the subscripts to generalize, F is equal to Fsat exponent V under bar of the liquid P minus P saturation over RT. All right, so important not to get these terms mixed up. So Fsat is the fugacity of the liquid at the temperature and pressure of saturation. P is the pressure of interest. I'm going to write these things down. So P of interest. This F is the fugacity of a vapor, or I'm sorry, fugacity of liquid or solid at a pressure of interest. And that's where this P of interest comes into play. All right, Fsat is the fugacity of saturated vapor. Fsat is fugacity of saturated vapor. Or, because we're at saturation, it's also the fugacity of the saturated liquid too. Of saturated liquid slash vapor, we'll say, at P star, at P sat. P sat is the saturation pressure at T, and this is assuming constant T. So remember, we have to assume that T is the same, doesn't change. All right, so plugging these things in to figure out what our final fugacity is. So I'm going to say that F is equal to F sat, and we said that was 0.0317 bar. And exponent of the molar volume, which was 18.054 centimeters cubed per mole. P minus P sat, remember the pressure that we want is 1,000 bar. Saturation pressure is 0.0317 bar. Over RT. Now the R that we're going to need is in bar centimeter cube per mole Kelvin. So that's 83.14 bar centimeter cube per mole Kelvin. And now we need the temperature in Kelvin. So that's 25 plus 273, so 298 Kelvin. All right, that's just a number that we can crunch, and working that out gets me that the fugacity of the liquid at 1,000 bar is, I get 0.0657 bar. All right, that's just our final answer. So again, just to recap, you use the Poynting correction. This is good for a solid or good for a liquid at high pressures, and we need to know what the fugacity and the saturation pressure is at the temperature of interest. Now, a couple more key points. I forgot to annotate. This is molar volume of liquid or solid. And obviously, if it's a solid, it'd be V under bar S instead of L. Molar volume of solid, and key that we assume it's constant with respect to T. Okay, so keep that in mind as well. One more thing that I'd like to mention is that if we do not know what the saturation fugacity is, this is where we'd need an equation of state. So you can reason this by saying that this F sat is the fugacity of the saturated liquid at equilibrium. Because it's saturated, it's also equal to the fugacity of the vapor. So you could also, you may need the equation of state, may need EOS to calculate the fugacity of saturation for the vapor phase. All right, so what you would do is you would apply this equation up here. Remember, if you have an equation of state, always you'd apply this equation first. So if you have a vapor, and you're more likely to have an equation of state for the vapor than you are for the liquid or the solid, use this equation of state to figure out what the fugacity of the vapor is. You apply that reasoning that at saturation, the fugacity of the vapor is equal to the fugacity of the liquid.